All right, so I'm Paul. In the last talk was talking about models, ensembles, boosting. He talked about evaluations. Thank God, because that's very important. So I'm going to go through kind of some of the other supervised techniques that we offer on the platform. And so everything that Paul talked about learning-wise was tree-based, right? But there are many approaches to machine learning that don't rely on decision trees. And so those are the approaches I'm going to talk about in this session. So at the beginning, for starters, let's talk about logistic regression. So remember, supervised learning. We have two kind of basic types of supervised machine learning problems. This is oversimplifying dramatically. There are a lot of other supervised machine learning sorts of problems. But these two basic types that we can solve are classification and regression. In classification, we're predicting a label, right? In regression, we're predicting a number. And so this is the objective variable. We can call it the label. But in regression problems, the label is numeric. Classification problems, the label is like a category. Okay, so logistic regression, what is it? Some potential confusion here is that, let's remember from the very beginning that logistic regression is a classification algorithm, which is bizarre, right? Because it has regression in the name. But no, you cannot use logistic regression to solve regression problems. I know, it's absurd. But this is taken from statistics that are very, very old, and so we have to continue to use this name. Even though it's a bit of a misnomer given current terminology. So using logistic regression, you can only use it to solve classification problems. Again, classification implies a discrete objective, so it implies you're predicting like a label or a category, something like that. And so how do we cast this as a regression problem? Like we said, regression algorithms are specifically designed to predict numeric objectives. So the fact that this is called logistic regression implies that we're going to use it to predict a numeric objective, even though we know, because I'm telling you, that you can only use it to predict classes. So how do we convert one thing into the other? So just as a kind of a review, if you don't know what linear regression is, hopefully you know what linear regression is. Basically, you fit a line into a cloud of points. In this case, it's a two-dimensional cloud of points. But in general, you can do multivariate linear regression and fit it into multiple dimensions if you want. You can see that this is a plot of BMI versus the skin thickness of your triceps. Generally, the skin thickness is a measure of your body fat, and your BMI is just a measure of how big you are. Generally, the two things correlate, right? If bigger people have more body fat than do smaller people. There are outliers, but in general, you can see a trend upward, right? As you get bigger, you have more body fat. And so one thing we can do here is we can fit a line to that cloud of points. We can, try to minimize the squared error against that line. So we try to minimize the distance all of those points are away from that line. And if we're very clever, we can do polynomial regression. So polynomial regression is just a generalization of linear regression. And that just means we fit essentially a different equation to this cloud of points. So we fit a squared polynomial or a cubic polynomial to this cloud of points. But it's basically the same thing. You have an equation. That equation has some free parameters. You fit those free parameters so that you minimize the distance that those points are away from that line. So again, this is regression. You have a cloud of points. You want to fit a line to that cloud of points so that it minimizes the distance that those points are away from the line. So linear regression, the equation looks like this. Those beta values are your free parameters. Those are the things we get to futz with, the knobs we get to turn to make that line move around so that it fits the points as well as possible. In quadratic regression, if we add a squared term to the regression, the equation looks like this. It gives us an extra free parameter, right? That beta 2 is a new parameter. So that means we have another knob to turn that will change the shape of our line a bit. In this case, quadratic regression, it'll change the curvature of that line to make it better fit the data points. And then decision tree regression, of course, is parameter free, right? the only parameters are the split points in the decision tree, and those are learned directly from the data. And the more data we have, the more we can split it, right? So the number of parameters in a decision tree is fixed not ahead of time, like it is with the linear and quadratic regression models. It's fixed when you get the data. It's fixed by the data itself. So that's an important difference between these regression algorithms and decision tree regression, is that with decision tree regression, the number of parameters you have can grow as you get more data points, because you get to split more and more. With linear regression, it's fixed at the very beginning. No matter how many more data points you have, you only have as many of those betas as you have features in the model, or features in the data. The number of parameters doesn't grow as you get more data points. With decision trees, it does. Okay. So now we want to do a classification problem that predicts some kind of binary value, either true or false, or 1 versus 0, to do like a categorical sort of prediction. And so can we come up with an equation up there, like that linear regression equation or like that quadratic regression equation, that we can fit to discrete data, that we can fit to data that only takes 2 values, true or false, or 1 or 0. So here's a little plot from the diabetes data set again. And we have all of the people who are false on the bottom there. Each one as a little circle, and all the people who have diabetes at the top there as a little red circle. And then they're plotted against their 2-hour blood glucose, so their 2-hour blood sugar reading. And you can see in general that as we move, let's see if I can use this. I'm afraid of using lasers. I'm afraid that I'll hurt myself or others. You can see that as we move this way, as your blood glucose gets higher, that you have a higher likelihood of having diabetes, which is an intuitive result, right? This is exactly the main symptom of the disease. And then as your blood glucose tends towards normal, it's less and less likely that you have the disease. So let's try fitting a line to that data. You can't, right? You can't fit a line to that data that's just not even close to a line. But like we were saying before, a line isn't our only option, right? We can come up with other equations that may be easier to fit to this data. And so what we want is like a function that looks like this, right? That has nice big flat parts on either side of the extremes that indicate that, okay, yes, down in the lower left-hand corner of the graph here, you should predict 0. And in the upper right-hand corner of the graph, as these values get higher, you should predict 1. That's something like we want to fit here, right? So this, it turns out, is an actual equation. This is the logistic function. And so if you plug those numbers into that equation, you get a graph that looks like that. As x here tends towards negative infinity, the probability goes to, the value of the function goes to 0, and as x trends upwards towards infinity, the value of the function goes to 1. So that behaves rather nicely, right? Big values give us 1, and low values give us 0. The only kind of problem there is that bit in the middle, right? Here, we have this big area where the output of the function is going to be neither 1 nor 0. It's going to be like 0.6 or something, which is not satisfying. That's not a 1 or a 0. That's not the prediction, right? That's neither of the two values that we're allowed to predict. We're trying to predict a label. So what can we do here? Let's change the problem a little bit. Let's imagine that we're modeling, instead of modeling the outcome, let's imagine we're modeling the probability that a person has diabetes. So really, what we're imagining here is that on this side, the probability that a person has diabetes is very close to 0. And this is true statistically, right? If you look at the points in this box, you've got a whole bunch of points where there's no chance of diabetes, and up here, or where there's patients without diabetes, and then just a few people with diabetes. So effectively, way down there on the graph, the probability is in fact 0. And also, if you look at the other side, effectively, the probability way up here is about 1. It's very, very high. And also, if you look in the middle, you've got sort of what you expect there as well. The probability is somewhere in between 0 and 1. It's not close to 0 for either of these eventualities. You've got roughly sort of the same number of people in the middle there. So if we're trying to model those probabilities, the logistic curve fits pretty well, right? The logistic curve here takes these intermediate values just where it's supposed to, and at the extremes, it takes the values close to 0 and 1. So it turns out we can model these probabilities pretty well with the logistic curve. So if we state this a little more precisely, logistic regression is a classification algorithm that works by converting the usual classification objective into a regression and then kind of spitting back out a probability and using that as its prediction. So there's a few caveats here. Whoops. So there's a few caveats here. One is that it assumes that the output is linearly related to the predictors, and we'll see what that means in a second. We have to see the exact form of the function it's trying to fit. And so the question is, how do we fit the logistic function to data? With linear regression, we have this very nice algorithm, ordinary least squares, and there are a bunch of other ones, but we can do this via matrix decomposition. We can find exactly the right fit for that line through the cloud of points. Logistic regression has a few more complications. And we're not going to go way deep into that, but we'll go into it a little tiny bit. Stephen Hawking has this great quote in A Brief History of Time where he says, you lose half of your audience every time you mention a mathematical equation. So he puts 1 in his famous book, and he assumes that he's going to lose half his audience, a single equation. So that's what we're going to do here. Oh my God, I think there might be 2 actually. Oh geez, wow, that's a lot. Okay. Yeah, so this is the logistic function. And here are these betas, again, are the knobs that we get to fiddle when we fit the logistic function. And so basically, you just do this transformation, and you get back out something that you can solve via the standard kind of linear regression sort of techniques. But the principle is basically the same. You have an intercept term, or what we call in logistic regression a bias term, that kind of moves your probability up globally, up or down globally, depending on the global distribution of the inputs. And then for each feature, you get a beta value, kind of a weight for that feature. So your job is to kind of decide with each feature how much you want to weigh it. If you think the feature is really relevant to classification, you turn that knob way up. If you think the feature is really irrelevant to classification, you turn the knob all the way down. And then, so this is the generalization I was talking about. You just get a beta for each feature, and you can solve this using basically the same techniques we use to solve linear regression once you do the transformation. And again, as I was saying, each of these betas are knobs you can turn a little bit depending on the relevance you think the feature has to the prediction. So as you move the betas down, you assume that they're negatively correlated. So if it has a large negative value, that means the feature itself is highly negatively correlated with the objective. The lower it goes, the more likely the objective is to be some class. And similarly, as you turn the knob up, you make the coefficients bigger and bigger, that means that feature is positively correlated with the probability of the objective class. These sizes shouldn't be confused with field importance, so they can really only be compared with one another. So if you have 2 different logistic regression models and you have some particular beta higher than 1 in another, then those are importances that you can compare. But if you have two different features, you can't really compare the values because the values that the betas take depend on the actual feature value. So it doesn't actually tell you which field is more important. It just kind of tells you, if you train multiple models, which fields are becoming more or less important depending on the different settings of those models. Okay, so a final comparison here, logistic regression versus decision trees. Again, logistic regression, you're fitting this curve, right? You're fitting the curve to the points. So it expects to draw this very smooth decision boundary that's a function, a linear function of the predictors. Decision trees expect no such thing. So that has pluses and minuses, right? If you have a nice, smooth, linear decision boundary, then logistic regression is really going to fit very well, and it's going to learn quickly because that's the assumption it's making, and so there's a lot of work that it doesn't have to do. Decision trees don't make that assumption, so if the assumption is true, you lose, right? Because you have to essentially relearn that assumption with decision trees. But if the decision boundary is very nonlinear, it's a very strange thing, you're out of luck with logistic regression, but with decision trees, it'll be able to handle it. Logistic regression can only learn this very specific thing, probabilities for discrete outcomes. Decision trees, you can kind of learn anything with decision trees. It's not it's a very adaptable algorithm that way. Logistic regression, you can screw up in a lot of ways if you futz with the parameters of logistic regression, and I'm not going to go into them here. There's a lot of documentation on BigML if you really want to get crazy with these. But if you futz with those too much, if you mess with the different types of regularization and scaling and codings, you can easily break the algorithm. Decision trees are pretty, oh goodness. Decision trees are pretty easy to not break, right? If you do nothing with decision trees, they'll do the right thing most of the time. And even if you increase the number of nodes to some gigantic number, or you decrease the node limit to something that's even a little bit above a trivial number of nodes, it'll do basically the right thing. Logistic regression is what we call a high bias algorithm, so it's slightly less prone to overfitting. Paul had that example where he added a single data point and it radically changed the first split of a decision tree. This doesn't happen with logistic regression. Because you're modeling kind of everything at the same time, you don't run into these situations where a single outlier will really influence the predictor a whole lot. And decision trees have the opposite problem. They're what we call a high variance algorithm. So you trade that stability in decision trees for more representational power. So you do have this problem with decision trees where you add outliers, they're very unstable, it changes the fit dramatically if you add a point just here or there. On the other hand, if you have this crazy decision boundary where you need to take these outliers into account, decision trees have got you covered. Logistic regression will require much more data to do a crazier fit like that. Because it fits a shape, logistic regression might work when there's less data available. So again, it makes this assumption that the decision boundary is a smooth linear function. You can fit a line with 2 points, right? In theory, you only need 2 points to determine a line. And so you can fit a logistic regression model with 2 points. If its assumptions are right, then that's all of the data that it needs. On the other hand, decision trees, they make these excess parallel splits, and so 2 points is going to give you a single split. The assumption is just a lot less general, right? With logistic regression, you're making this linear assumption, which is kind of a usual thing. A linear combination of features to make some prediction is something that gets trotted out a lot and works with a lot of different kind of standard data. Decision trees only start to get powerful as you add kind of a whole bunch of data into them, where it has enough data where it can make a whole bunch of splits and get a nice read on that decision boundary. So summing up, logistic regression is a classification algorithm. It can't solve numeric objectives, so don't ask it to try. It expects a linear relationship between the features and the objective, and so if you don't have that, logistic regression will not give you what you want. Logistic regression outputs a set of coefficients, and the scale relates to the impact, and the sign of the coefficients tells you whether they're positively or negatively correlated. And I trained a logistic regression model on that churn data just a few minutes ago. And so when you look at the logistic regression model on the churn data, it looks like this. Make it a bit larger here. And so you can see, instead of getting the partial dependency plot that you were seeing with the other model types here, because logistic regression is very nicely mathematically formulated, we can draw these curves that tell you precisely how the probability is going to vary as you change different features. So here you can see this feature on the bottom is the bill amount for the last month, and then the two curves represent the probabilities of the two different outcomes, whether someone does churn from the service or whether they do not. And so you can see this red curve at the bottom, yes, they do churn from the service, slowly slopes upwards as the last month's bill increases. And you can look at this relationship for any of these features. You see calls to support, I guess. You can see that as they make more calls to support, the probability that they're going to churn increases. And one of the things that this shows is this nice smooth decision boundary, right? Like when a person makes an extra call to support, so here they've made 2 calls to support and they get some probability, you don't get massive discontinuities here. It's even more obvious when you look at minutes used. Minutes used turns out not to impact the decision. If we go to last month's bill, here, okay, yeah. Here, so when you've used 160 minutes, the probability that you're going to churn is around 5%, all other things being equal. And then when you go up to 180, it moves to 7%. You don't have these massive discontinuities in probability at threshold points, right? With decision trees, that's the behavior you're going to get, because decision trees have drawn these splits. Even with ensembles of decision trees, the ensembles are composed of axis parallel splits. So you will cross a threshold, and all of a sudden the probability will jump up. And then you'll cross another threshold, and then there will be another jump. And in between those jumps in probability, it'll be static when you move around the value for that feature, right? So the prediction, the probability for the prediction will have this staircase behavior, where it's static for a while and then it jumps when you cross a threshold. That's just the nature of the model. That's how it makes decisions. If you're concerned about kind of smoothness as you move your feature values around, logistic regression is one way to get that sort of smoothness as you move feature values around. There will be none of these big jumps in probability. And people are concerned about that. Like again, going back to my time in the stock markets, like my manager, my boss, who was watching my trade operate, would freak out when suddenly it would say, no, I don't want to trade, no, I don't want to trade, no, I don't want to trade, and then something would tick up, and it would be like, okay, now's a good time to trade. Like, that's not a behavior that's satisfying for somebody, right? When there's a very small change in outputs, and you see this large change in behavior, it can be disconcerting for people. But again, that's the nature of decision trees. That's exactly how they work. A tiny change in the output is going to put you on one side or the other of that threshold, and you're going to experience a discontinuity in the output probability of the model. Can you? I was looking for it. Where is it? It's not this one, is it? Where? Oh, yeah, okay, yeah, there you get it back. So here's another view. You can see how smooth the decision boundary is here too, right? Here we're looking at 2 variables, and you can see how gradually the colors change around the decision boundary. That actually looks a lot better up here than it does on my screen. That's nice. Okay. Okay, so moving into the kind of the last supervised learning technical talk, if I can figure out how to do it. Yeah, let's do that. All right. So the last two algorithms, supervised algorithms that we're going to talk about are Deepnets and time series. And with Deepnets and time series, we sort of start to push at various frontiers of what we've been able to do so far with these models. So with Deepnets, we're going to kind of push hypothesis space. We're going to push this idea of the possible structures we can learn kind of out towards its limits. And with time series, we're going to push in the other direction in the sort of input data, in the sort of prediction problems we're trying to solve. So let's start with deep networks first. So the way BigML deep networks work is just basically to try to provide you and your data the most powerful machine learning algorithm we can build. Why do we need another supervised learning algorithm? Well, first of all, deep neural networks give state-of-the-art results in things like vision, speech recognition, NLP. These problems are typically the domain of like Google and Microsoft. They are the ones who have billions of data points to train these vision models and so on and so forth. And so there's a notion out there that these models are only for those problems, right, where you have billions of data points. Because they're so powerful, in general, they've been difficult for people to come with sort of average data where you've only got thousands or tens of thousands of data points and try to train a network that works for them. So the goals of our deep nets, right now we're not doing CNNs, although CNNs are coming in the next month or two, maybe three months. We're not doing recurrent networks yet. But these networks solve a particular type of subproblem, right? Convolutional networks are usually used for kind of signal processing problems like vision or speech recognition or even text if you've got word embeddings for your documents. But convolutional networks only work if you have sort of these signal analysis problems, which again, most people's data is not a signal analysis problem. And LSTMs only work if you've got a sequence problem, which again, most people's data sets are not precisely sequence problems. So this is why we don't offer these things yet, is they're usually specifically engineered to solve one type of problem. And you've got to change the engineering depending on the problem type that you have. But having said that, like, is there a way to bring the power of deep neural networks, most of the power of deep neural networks, that doesn't require that problem-specific engineering to your problem without me knowing anything about your problem? So you being able to approach the platform and do it yourself. And, yes, there is a way to do that. And so, first of all, the way this bit of the talk is kind of structured is I'm going to try to separate deep learning myth from reality. So myth number one is like the kind of apocalypse view of neural networks, that they're absolutely the greatest thing in machine learning, or they spell the end of the human race. Really, what deep neural networks are again just another type of supervised classifier. As Paul had, a diagram that was reasonably accurate at the beginning of his first session, where he showed, machine learning and deep neural networks is just kind of a smaller bubble inside of machine learning. That's really all it is kind of a subfield where we're doing several specific things. So how do we motivate deep neural networks? How do we say, okay, this is how they're different from all other learning algorithms? Well, let's think about trees first. So trees, as we said before, massive representational power, right? You can, as you plow data into trees, they can split and split and split, and they can grow to accommodate any sort of prediction surface, any sort of decision surface that you have. So that's super nice. They're also really fast at searching through this space of possible splits. Unfortunately, as we said before, to represent smooth functions of more than one variable, so if you've got a line or some kind of a continuous function representing your decision boundary, that's not what decision trees do. Decision trees do these axis-aligned parallel splits that don't take into account more than one variable at a time. And so when you've got these multivariate functions, smooth functions of more than one variable, difficult to represent in decision trees, they require more data. And so we come along with ensembles to help mitigate some of those difficulties, right? Ensembles do the thing where you build multiple models on subsets of the data, so it has the benefit of smoothing out some of that variance that you would get from a single tree, and it also has a smoothing effect, so you can learn some kind of better approximation of smooth functions of variables. So we just learned about logistic regression. So let's think about some of the pros and cons of logistic regression. Again, logistic regression makes these nice linear assumptions that makes it so that a collection of smooth multivariate functions isn't a problem, right? If you've got a nice linear function where all of your features can be mapped via weights onto your prediction, then you're all set. That's what linear regression assumes to begin with, and so that's the sort of function it's going to fit. If your data does meet that assumption, then it goes super fast because it can do a lot of shortcuts to optimizing that function because that's the only function it's considering, right? It's not like decision trees where it's kind of considering all possible functions based on how much you split on the data. Logistic regression reduces the space of the function it considers, and so that makes it very fast to find the right version of that function. Unfortunately, it's parametric. So if your data doesn't meet the assumptions of logistic regression, then you're out of luck. Decision trees, you can just feed it more data until it finally gets the point. Logistic regression, you can't pull that trick. So is there a way we can use kind of cleverness in the same way we used ensembles to mitigate some of the problems with trees? Is there a same way we can use some of that cleverness as machine learning academics to mitigate some of the problems with logistic regression? And so this is one way you can choose to think about deep nets, is just a generalization of logistic regression. So one way you can choose to think about ensembles is a generalization of trees, right? Well, a single tree is really a special case of an ensemble. It's an ensemble with only one tree, learned on all the data. And so if we think about logistic regression, we can think of it, if we want, as a special case of a deep neural network. So this is a way to view logistic regression, right? You have your inputs, you have a weight for each of your inputs depending on the class, and the weight is high if that input correlates with that class. The weight is low if that input does not correlate with that class. So here I've got 3 output variables. So this is a multi-class problem. I have 3 outputs instead of a single binary output. I have 3 binary outputs, right? I have red, blue, or green, or some kind of a labeling problem like that. So I have 3 outputs instead of binary outputs. And so for each output, I have a weight. That's what these arrows represent. For each output, I have a weight on each input. And again, the weight is positive if that input is correlated with that output. Weight's negative if it's negatively correlated with that output. And the weight is 0 if it's not correlated at all. And so each of these arrows here represents one of those betas, one of those knobs I get to tune to maximize the performance of my logistic regression model on the training data. And so this is, good as far as it goes. And then, so yeah, each of those, I've got the mark W here. On other slides, they're beta. I'm sorry for the inconsistency. But yeah, the W represents one of the knobs I can turn. And then at the top there, I apply the logistic function, as I said. So once you do the linear combination of variables, you apply the logistic function, you get the probability for that class. So this is logistic regression, just kind of laid out in a different way. Okay, now what I can do is I can introduce a whole bunch of intermediate computations. So here I have a weighted, in this middle layer of circles, oh, there's so many pointers. In this middle layer of circles, I have an aggregation of the inputs, right? I have a weight for each input given by these arrows. And here, I'm going to apply some sort of function to the weighted combination of the inputs. And I'm going to do that for every single one of these nodes. And then the output probabilities are finally going to be based on these intermediate numbers that I've computed in the middle. This seems like unnecessary computation, right? Like, why am I introducing this inner layer of dot products? Why am I introducing? There seems to be no reason for this. It's just another level of separation from the outputs and the inputs. In reality, the reason you do this, the reason you introduce this hidden layer, is because it expands the possibility of functions you can represent. So there's mathematical proofs out there that show that if you add enough hidden layers, you can represent any sort of decision surface in the same way that decision trees can as you plow enough data in. If you give decision trees infinite data, they can represent any decision surface. Similarly, as you can add nodes in the middle there into this logistic regression thing, And you can eventually, given those nodes, you can approximate any decision surface. So it expands the hypothesis space, right? It expands the number of things we can possibly try to fit our training data as closely as possible. And in the middle there, we apply a function just like we do at the top layer. But now we've got a whole bunch of parameters, right? Logistic regression had a few parameters that you could screw up, but now, how many hidden nodes do we want? How many hidden layers do we want? We could apply something other than the logistic function there. We can, common choices are the inverse tangent and rectified linear units, and there's all sorts of different functions you could apply there other than the logistic function. So that becomes a problem, because getting that architecture right is kind of at the heart of what makes deep learning interesting, right? If you can find the right architecture for your problem, that's how you get a good deep learning model. And so this is the second myth, is that deep neural networks are great for these marquee applications for vision, speech recognition, a few different text things, but they're less interesting for kind of the general machine learning problem, right? For those, you should use something else. You should use XGBoost or whatever software you've heard about. My own feeling is that the only reason that people don't use deep networks is because they're so difficult to parameterize. So just as an example, here's gradient descent algorithms, the algorithms you use to optimize a network once you've structured it. Most people don't know what any of those things are. How many hidden layers do you want? This is the list of functions you could possibly apply at each node, and so on and so forth. Like, there's just a dozen things, and I can tell you for most of these things a way to screw up your network pretty good, a value you could take that would just break everything in any of these. And there's just so many. And that doesn't even get to parameters that are specific to that descent algorithm, like the learning rate and the momentum and blah, 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 blah. It's just a nightmare of parameters. And every single parameter is usually a pitfall, right? Usually, there's not like a magic value that makes things really good. Usually there's several magic values that make things really bad. And so it's just not interesting at all to try to optimize these things when every knob you turn seems to make things worse. And so clearly there's too many parameters to do this by hand, right? There's just dozens and dozens of these things. Nobody, including deep learning experts, really has a comprehensive idea of how they work altogether. There's not a lot of theory in deep learning yet. There's try it and see if it works. So setting them takes kind of significant domain knowledge. And so we at BigML take these couple of steps to try to help this process out. First of all, we do meta-learning, which, given your data, we make a good initial guess. I'm not going to talk too much about how we do that, but basically, we learned hundreds of thousands of neural networks over dozens of different data sets, and we measured the performance of all of those things, literally about 300,000 networks. And so when you come with your data, we make some measurements. We say, okay, you have this many features, this many are numeric, this many are categorical, this is what the distribution of your class looks like, and we try to choose a decent network structure based on those attributes of your data. And then another solution is just network search. So if that first one that we try doesn't work, we just try a whole bunch, and we measure the performance as we go. And I'll get a little more into that right now. And so this is what Bayesian parameter optimization does, and this is kind of this is how we optimize the structure of these networks, but as Paul mentioned in one of the earlier talks, we can use this to optimize kind of any collection of machine learning algorithms, to optimize against any collection of machine learning algorithms. And so whenever you see something like AutoML or automatic machine learning optimization or whatever, this is almost always what it's doing, unless it's doing something that's not as clever as this. So the basic idea here is we have all these possible structures, right? And to begin with, we just make up some random structures. We have that good initial guess. We try a few that are quite different from that good initial guess, and we're just going to model and evaluate them all, just the same as you would in BigML. We're going to split it into a training and test set. We're going to model on part of the data. We're going to test on the other part of the data, and we're going to get some performance number out. And so, this one has a performance of 0.75 on whatever, however you choose to measure it. Then the next structure there, model and evaluate, that one's worse. Hey, that one's pretty good. And so based on the results of that, we can make a model. We can say, okay, this structure did well, this structure did poorly. What are the differences between those two structures? And then we can reorder our queue of possible structures here so that the ones that look good, according to what we've done so far, move up in the queue, right? And so we evaluate the most promising ones sooner. And there's a little bit of nuance. You have to, like, you don't want to take the same structure over and over again. You want to evaluate ones that are a bit different from one another so you continue to explore the space. So you don't just take the best one all the time. You take the one that looks really good, but it's also different from what you've tried before. But the spirit of the algorithm is basically the same. You're modeling and evaluating with a bunch of different neural network structures, and then you're using the results to motivate the choice of the next ones to model and evaluate. And you just keep doing this until you're bored. Okay, benchmarking, is this even necessary? What time is it? So this is just a little aside about benchmarking. If somebody comes to you and says, we built the best machine learning algorithm, like general purpose machine learning algorithm, usually they're wrong because they haven't done the test with enough data sets, they haven't done many iterations of cross-validation, and typically they've only measured with one metric. So they're like, oh, we're getting better accuracy on these 20 data sets. First of all, accuracy is broken in the way that Paul mentioned before. And second of all, using any one metric is usually not enough to give you a general picture of whether or not something's better or worse than something else. And so this is a benchmark I did. There's more than 50 data sets. We're comparing them on 10 different metrics and comparing 30 different algorithms. So a whole bunch of the usual suspects from R, scikit, Weka, XGBoost. And you can go to it here, but the upshot, I think I still have that, yeah. And there's kind of a lot to explore here. It's actually a really interesting little thing that I built, and I'm not just saying that because I built it. I find the results very interesting. But here, you can see the BigML deep neural networks do in fact outperform everything. And this is just off the shelf, right? This is what you can do in one click. So the criticism that professionals in machine learning would level against something like this is, oh, you're just using the random forest off the shelf. If you were able to parameter tune a little bit, you would get better performance from random forest. And that might be true, but that means I have to go into the software and fiddle with knobs and write code, and I don't want to do that. I just want things to work from the jump. And so deep neural networks kind of realize that promise as well as it can be realized. It beats everything else without any parameter tuning. And again, we're evaluating these on a bunch of different things. Here's all the data sets we're using. Obviously, there's a ton. And then if you really want to dig down into it, under here, you can see how every single one of these algorithms did on every single one of these data sets. So you get to see exactly where algorithms fail and where they don't. And yeah, that can be kind of an interesting, for those of you who are interested in weaknesses of algorithms, this is an interesting exercise. Like this occupancy data set here is a relatively easy problem, but the only things that get it right are very simple algorithms, decision trees, LDA, linear regression, or logistic regression. So this data set is like a very strange data set, right? You can see that usually these are the usual suspects, random tree algorithms, deep neural networks. Usually they do the best out of everything. That's what the very dark stripes mean. But on certain data sets, they just fail to do well where very simple things tend to do well. And so that leads kind of nicely into the last point here. Actually, this isn't the last point. So myth number 3, deep neural networks aren't interpretable. Yeah, I mean, that's true in a sense, right? You can't look at them and know exactly what they're deciding like you can with decision trees. But explainability has kind of come a long way in just the last 3 or 4 years. So recent work in model interpretation just kind of applies to models in general. People have gotten the idea that if a technique for interpreting a model doesn't work for kind of any model, that it's not really that good. You want like a model-neutral way of interpreting a model's predictions. And so we have feature importance measures that try to capture that model-neutral notion of feature importance. And also we have a prediction explanation functionality that will give feature importance just for a single prediction. And that notion is, again, model-neutral. Most of these, I'm not going to go into how this is computed exactly, but most techniques for this, including ours, rely around kind of perturbing data points, changing the feature values a little bit, and then predicting and seeing how much the prediction changes. If you perturb a feature value, if you move a feature value and the prediction changes a lot, then obviously that feature value is very relevant to the given prediction. And I wanted to show that off just a little bit. Do you know when I'm supposed to finish? Now? Oh,
Yeah, now it's time for lunch, but if you have, we can start the lunch a few minutes later.
I don't want to keep people from lunch, that's cruel. Yeah, no, I'm nearly done with this section, so we can put the other section somewhere else. Yeah, so I was just going to show prediction importance briefly here. So here's a deep neural network that I've trained ahead of time on the churn data again. Here you can see the decision boundary, which is very much nonlinear, right? So we've managed to capture nonlinearity in the decision boundary with the deep neural network. But if I go up here, this says Deepnet summary report. And if I click on that, you can get a notion of the overall feature importance for the model. So here, in this particular model, website visits was the most important feature. The number of times the person visited the company website. A little less than that was support calls, and then less still than that was the amount of their last month's bill. So this has nothing to do with the actual data, or it's only tangentially related to the actual data, but more this is just saying this is what the model is basing its predictions on, for better or worse. It might not be what you expect, but these are the features that the model is relying on. And so that's good. That gives you an idea of overall what features the model is relying on. But for a given prediction, that might be different. So if I go here to predict with this model, it'll give me the form that Paul showed you before. And let's say the person didn't visit the website at all, right? But let's say they made a whole bunch of calls to support, and let's say their last month's bill was like $300. And so now you've got a case where the person's not visiting the website, but that's the most important feature for the model, right? We just saw that in the feature importance plot. But if I use prediction explanation here, and I predict, you can see that now the support calls happens to be the most important feature for that prediction, right? That's the feature that the model was looking at, saying, hey, they made more than 2 support calls. That's the most important thing about this prediction. That's what changes the value the most. If you change this number, the prediction will change a lot, essentially. And then second is the last month bill. It's greater than $250. That's the second most important thing to this prediction. And you see, if you sum these two numbers, the numbers are kind of designed to be added up. So there's oh geez, that's not very visible, but that's 63% and 34%. So you can see we're capturing the vast amount of possible change to the prediction with just changes to those 2 features. So if everything else, if those 2 features are kept the same and you vary everything else, you won't get very much play in the value of the prediction. Yeah. So that's what prediction explanation looks like. So a bit of a myth that deep learning models are all uninterpretable because people have been, researchers, academics have been kind of champing at the bit at this exact problem for 5 years or so, and they have made some headway in being able to interpret the predictions of those models. And then the very last thing, so I showed you that benchmark. So deep learning algorithms, as long as you're willing to develop this thing for automatically configuring them, and you're willing to trust that thing, they perform very, very well, right, relative to other model types. And so why not just use deep learning all the time, You know, it seems to perform pretty much as well as everything else for most problems, and for some problems it performs spectacularly better than anything else. So why not just use it for everything? Because there's things other than performance on the data to worry about. So if you have small data, you know, where small could still be thousands of points, depending on the problem that you have and the number of features that you have. If you have small data, you get to those overfitting problems with deep neural networks, where if you make a gigantic structure, you try to optimize it against a few hundred data points, it's going to be overfit. You're not going to generalize well. Problems where you could benefit by iterating quickly. So these deep learning models are slower to fit by quite a lot than a single tree or a single logistic regression. So if you have a problem where you can, you know, it takes, you've got hundreds of thousands of data points. It would take a deep network like an hour to fit all those data points, or millions of data points. Logistic regression, it just takes a minute or two. You've got another hour where you could be engineering new features if the model's performance wasn't adequate. So problems where you need to iterate quickly, you should just, you know, dumb down to a simpler model, iterate against that simpler model, and then when you're sure you've got decent features, you can always kind of complexify to deep learning to try to get better performance. And then problems that are easy, or for which top-line performance doesn't matter. So if you've got a logistic regression model, and it's predicting with 98% accuracy, and, you know, that makes you $1 million, and a deep net that predicts with 99% accuracy makes you $1,001,001, you should just use the logistic regression. Like, first of all, it's lower bias. You can guarantee pretty much that it won't be overfit. And second of all, like, it's faster. Pretty much everything about it is better, other than it doesn't get as high a performance. And so if that nominal increase in performance doesn't matter to you, you should always use the simpler thing. And kind of the big takeaway to remember about deep learning is that it's just another sort of supervised learning algorithm. So you should be evaluating it as such. If you need something to go fast, if you need it to go fast, deep learning may be not for you, right? Again, unless the performance increase justifies the decrease in speed. But if you're making tens of thousands of predictions per second, as some of our clients are, deep learning just isn't fast enough for you. And so, again, it's just another supervised algorithm. It can always be swapped out for the thing that's faster. And here's a little quote from Stuart Russell that kind of puts deep learning into perspective. Things that have been around for 20 years, the recent advances are mainly engineering advances. So more data, better computers, and better programming languages for deep learning are what have driven the deep learning revolution, more so than like actual academic progress.
All right. Yeah, so as Maria said, if you recall, last time I was up here, I was supposed to talk about time series, and I didn't. I lied to you all, and so I'm trying to make good on my promise and talk about time series. So it's not totally out of bounds that I'm talking about it now, because even though it is more of a supervised case, it's different from the supervised cases that we were talking about yesterday. So in particular, machine learning has this assumption that we all call the IID assumption. How many people know about the IID assumption? Just one of you. Paul. Bravo, Paul. Yeah, so the IID assumption, so it's the two I's are independent and identical, and the two things we're claiming here is that when you draw a data point for your training data, there's some magical distribution that's generating this training data, and you draw all of these points independently. So you just sample the training data over and over again. The point you draw now doesn't depend on the point you drew in the last time you picked a point. So they're all independent of one another. And they're identically distributed, so they all come from this magical distribution of the training data. But first of all, in the real world, that's almost never true. This is an oversimplifying assumption. It only works, it still works some of the time, even when it's violated a little bit. And so you can still do supervised learning in some cases. But in the real world, most data, all data does not obey this assumption, and sometimes it's kind of dramatically violated. So for example, if the data you have is in a sequence, and the last value of the sequence depends on the history of the data, then you're kind of really throwing that assumption out the window. You have to do something else. You can't do the usual supervised learning things. And so a good example here is if you're trying to predict how quickly the battery level is going to go down on your phone. So the battery level on your phone, starts at full, and then it decreases in kind of this power law type of curve gradually to 0, right? The power level on your phone depends very much on what happened before, right? If your phone has been unplugged from the wall for 3 hours, it's very different from if your phone has been unplugged from the wall for 1 hour, right? It depends on how many points you have in the past. That's the level of power in your phone. And similarly for businesses, like the sales at businesses tend to grow over time if they're doing things right. And so your sales from last year very much influence what your sales are going to be this year, right? Your business is growing. You're assuming they're going to be either 5% more, or if things go badly, they're going to be 5% less. Your sales are not going to be at a level completely divorced from last year's sales. And so here's another way of saying that same thing. Here we have machine learning data of the usual type. So I have all of these objects. I know what color they are. I know how much they weigh. And based on those two features, I'm going to decide what type of object it is. It's either a pen, an apple, or a pineapple. This is one of our engineers made up this example, and I find it charming somehow. And so the deal here is that in the usual supervised learning case, we can discover patterns in this data, right? If something is red and it's a certain size, then it's an apple. If something is not blue, then it's maybe a pineapple, and so on and so forth. And the key here is that when you reshuffle the data, so you change the ordering of the data, the patterns are the same, right? We're treating each row independently. The data obeys that IID assumption. All of the points are independent from one another. Now, let's say we have a pineapple harvest, right? So we have many years of pineapple harvest, and we have the pineapple harvest as it goes on. Now, as the years go on, more pineapple trees are planted. The pineapple orchard, I don't know what you call it. Is that a pineapple orchard? A pineapple grove? The pineapple plantation, the farm, gets bigger and bigger, and so over time the pineapple harvest grows. And so you can see this plot. A lot of plots look like this. You look at stock markets over many years, or you look at, this is kind of a population growth. You look at curves like this. A lot of curves have, again, these logarithmic distributions. And so the key here is there's this kind of general trend, right? You can't really make a prediction from these points unless you take this trend into account. The trend is very important. That's really the only thing that's allowing you to make this prediction accurately. And so if we reshuffle the data, obviously this is totally broken, right? We reshuffle the data and now there's no trend. There's really no way to make this prediction. All the points are random. It's not like the rows are correlated with one another, right? I mean, a little bit. But if you reshuffle the points, you lose information. And so the key here with time series is that we're going to try to use data from the past to predict the future, right? This is kind of different from the usual machine learning case. In the usual machine learning case, we still gather training data from the past and use it to predict the future, but we're imagining that the future out quite a ways from the present is going to be basically the same as we go forward, right? Our distribution of data is not going to change over time. And so how do we do that? So the first kind of basic trick is these exponentially smooth models. And what that means is that we're going to look, 1, 2, 3, 4, 5, several instances in the past. We're going to apply this weighted average over those last few points. And so we get a curve like this that, of course, does basically the right thing, right? Because the past informs the future. The past, or the future in these problems is never that different from the immediate past. So that's like the right thing to do on a high level. And then we try to account for these other factors. There's 3 factors that we try to account for, and this is the implementation that BigML has rolled of this particular thing is kind of the standard univariate time series solution, the one you would get if you went to an R package or a Python package or something like that. And we think about these 3 factors. First is the trend. Sorry. And we can either think about the trend in one of 2 ways. The first is additive, meaning that over time there's this linear relationship between the objective and the time component, so that it's going up in this linear fashion. And then the other one is multiplicative, where it's going up in a logarithmic way. And then we also have seasonality. So seasonality is our word for kind of any sort of cyclic behavior in the signal. And the seasonality can also be additive or multiplicative. So additive, the seasonality is goes up with time, but in this linear way. And again, multiplicative, you see those differences are also increasing as the sequence goes up. So the seasonality effect grows with the magnitude of the sequence. And then error. So in these kind of baseline statistical models, we often have an error term. So anything that can't be explained by trend or seasonality, we try to explain, we lump it all into this 3rd category called error. And error also comes in 2 flavors, either additive, meaning that the error we get from the trend we expect is independent of the absolute value of the sequence, and multiplicative, meaning that as the sequence goes up, that the error also increases. And so you can see that we have these 3 terms, and either one can be not there at all, or multiplicative, or additive. And there's actually a so each one of these types of models we can denote by this 3-letter acronym, right? Depending on what our error is, what our trend is, and what our seasonality is. And so all of these could be different. They don't all have to be, multiplicative or additive or not present at all. They can all be different. And then also, we have this D term, so AD or MD means multiplicative damped, or additive damped, meaning that the trend, if the trend isn't increasing, it tends to revert to its mean. So there's this damping term that makes sure everything doesn't just get totally out of control as time goes by. So any of those things that I mentioned, error, trend, and seasonality, can all take these different values, the none or multiplicative or additive, or in some cases the damped version of multiplicative and additive. And so you see we have these tables. Basically each one of these tables, or each entry in this table, represents a type of model we could learn. And so because there are not very many of them, like with a lot of our model types, as you parameterize them, you could have an infinite number of possible values. There are like hundreds and hundreds of values for node threshold and for number of trees and ensembles. Here we have kind of a manageable number of total models we could possibly learn. And so BigML in the background just tries them all. And then we produce a number of goodness of fit metrics after we try them all. So there's a few things here. You don't have to worry too much about these. But basically, the first 3, as you add parameters, there's a penalty for adding that complexity. So just like anything else, as you add parameters, there's a tendency to overfit, right? You add parameters, you add flexibility to the model, but with that flexibility, you can fit the data too closely. And so the first 3 of those, AIC, AICC, and BIC, all are ways of penalizing extra complexity in the model. R squared, of course, does not penalize complexity. It just looks for how closely you're fitting the training data. Okay, so let's see that very, very briefly here. And so here I have this data set, and what this is monthly milk production from all of the cows in Croatia, I think, for like the 1960s and 70s. For some reason, this data set is canonical in the univariate time series world. Again, something that I find a little bit charming. you really want to know how much milk they're making in Croatia in the 70s. Yeah, so here's this data set, and it's basically what you expect. It has a date, and then for each date, it has the number of pounds of milk that you produced in that month. And I think it's on a per cow basis. And so, you know, we go through the usual steps. I'm not going to go through them again, but we make a data set out of this, and then we just go to one click. If we went to one click time series, BigML would just kind of know what to do with this data, and we would get this model. And so you can see right away the data is cyclic, right? Cows do not give the same amount of milk all of the time. They tend to, you know, give more during certain seasons than other seasons for various agricultural reasons. But you can see the cyclic nature of the data. And then also, you can see that the trend is generally increasing, right? Even though this is on a per cow basis, like they're figuring out in Croatia how to get your cow to give more and more milk over time. And so milk production increases over time and also continues to have this seasonality component. And you can see down here the model that we've selected takes those things into account. So it has an additive trend, which you can see is about right. The data is going up linearly in general. The error terms, again, that's a little more difficult to see, but the kind of jitter around the correct values here is a little smaller than the jitter around the correct values here. And then also additive seasonality, so there's a seasonality that also increases as the sequence goes up. But down here, if I expand this models, you can see that we've learned all of them. So we've tried to fit all of these models, and this happens to be the best one in terms of the various metrics that we track. But all of these other ones have some level of fit as well. And so you can see that most of these models perform about the same according to most of these metrics. And then there's kind of like a cliff here where we stop taking certain things into account, right? Which ones is it? This is the trend and seasonality. So here is the model we get if we don't take into account the trend and seasonality. And you can see it's significantly worse than the ones where we do take into account trend and seasonality. And if I check one of those, I can actually see, you can see that this is kind of it's kind of one of those 3D pictures, right? But the darker curve lags the lighter curve because, again, we're not taking into account trend or seasonality, so we can't see this coming. No matter what it is, we're always lagged because we're just using that exponential model. When we use more information than the exponential model, when we take into account the trend and seasonality, we kind of know, depending on where in the year we are and where in the overall curve we are, we kind of know where it's going, right? If I'm at one of these peaks, I'm like, okay, it's not just gonna continue up, like if you did an exponential model that just based its prediction on the last few points. It's going up and up and up. Oh, it's going to continue to go up. That's what's going to happen. But if the model takes into account the seasonality, and no, it reaches this peak, and then it starts to go down. So then you don't, on the lighter curve, you're taking into account seasonality, you don't get this lag. And so that's basically the time series model that we're offering right now. Hopefully, within the next year, we're going to kind of expand our time series offerings. But something important, you know, to know about our time series models, these ones, is this is like the canonical univariate time series model. So it can't do multiple sequences, for example, that are all running in parallel. That's something that we don't do right now, but we're going to do in kind of the near future. But if you have one of these univariate problems, this can be very powerful because it fits all of these different model types and can, if you have data that has trend and seasonality components, this will do very well. It's very much like logistic regression in that way. It makes a bunch of assumptions about your data. If those assumptions are right, the performance is amazing. If those assumptions are incorrect, you can't really use it. And then the last thing I'm going to mention about time series yeah, so these are the metrics again. Oh, before this actually. So of course, the interesting thing you want to know about time series is what is the series going to look like in the future. And so we have this forecast horizon here that will allow you to look into the future. And you can see, here's the model that's not taking into account trend or seasonality. What does it think the future is going to be like? Just like the recent past, right? It just thinks that's going to continue into infinity. But you can see when we take into account trend and seasonality, the other model, even in the absence of a lot of the future information, still has a good idea, probably, about what's really going to happen. So that's kind of the power of these trend and seasonality components, is that if you know the data is reliably trending and seasonal, you can do a good prediction, or you can do a good job predicting maybe years into the future without any information. So these shaded areas are confidence bounds. So you can see this model that's not taking into account trend and seasonality, the confidence bounds are enormous, right? Because it's getting more and more unsure about what's going to happen. It has no information that would allow it to make a good prediction about the future, in the absence of that trend and seasonality data. Whereas the confidence bounds in the model that does take into account trend and seasonality, the confidence bounds are increasing much more slowly. They're still increasing because as you get away from the current moment, your prediction gets more and more uncertain. But because you have that information about the trend and about the seasonality, you still have some confidence about what's going to happen numerically. And so the last thing I wanted to mention is this linear splitting, right? Paul talked about data set classifier evaluations in several talks ago. He talked about how you do a training and test split, right? You never want to evaluate the model on your training data. That's still true here. When you do a training and test split, though, you have to be particularly careful with time series data not to do a random split. Again, how come? Because all of the data points have information about all of the data points around them, right? So if you do just a random split, you're pulling data that you're pulling information from the training set into the test set and vice versa, and that you don't want. And so we have to do this linear split thing, and these are both first-class options in the interface. Like when you go to do a split, you get to pick whether it's a random split or a linear split. And when you're evaluating data that has this time series component, you always want to make sure you're doing this linear split. You're training on data from the past and testing on data from the future. Otherwise, you won't get the right performance numbers. And this can also be important. I think Paul mentioned it in the context of a data set earlier. It was the Oscars data set, where Paul mentioned that this was another data set that has this time component, right? You can imagine that predictions from the same year have information about one another. So maybe 10 years ago, the Oscars really followed the Golden Globes. There were a lot of shared voters between the Golden Globes and the Oscars, and so those awards were more correlated then. And so you don't want to take half the awards from that year and use those to train and predict the other half of the awards from that same year, because you'll never get to take some awards from one year to predict awards from the same year. You get all of those at the same time. You never get to know any of the future in advance. And so there are a lot of other cases like this where you want to make sure to split your data between the past and the future to make sure information from one time period doesn't leak into the other time period. All right. So that's my little spiel on time series. I could, talk about other things related to time series for hours up here. Like there are ways to convert those multivariate time series problems into ordinary classification problems, and so you can use some of the techniques from regular old classification to solve certain types of time series problems. I'm not going to talk about that, but this isn't the only thing you can do with time series data. If you say, oh, I have multivariate time series data, can I still use BigML? Yes, you can still use BigML. You just have to be kind of clever about transforming your features and, again, making sure data doesn't leak from the past into the future and give you the wrong idea about your model's performance.